In this example, we're going to be evaluating the triple integral over the solid E of z times the square root of x squared plus y squared plus z squared dv, where E is going to be the solid bounded above by the sphere x squared plus y squared plus z squared is equal to 16, and below by the cone z equals the square root of x squared plus y squared. Now, in our first video, I mentioned that both spheres as well as cones tend to look pretty good in both cylindrical as well as spherical coordinates. However, I also said in our second video that the very first thing that we should do in any of these situations is analyze the xy trace. Now, as far as the xy trace is concerned, I see that both of our curves are going to contain an x squared plus y squared somewhere in there, definitely indicating that this is going to be a pretty solid choice as far as conversion to polar goes. Now, for a proper xy trace, though, we need to be setting z equal to a constant. Now, you'll notice that we were not told any constants in here. We were simply told that these two surfaces are going to be bounding our region. As such, we're going to need the curve of intersection for these two regions. So what I'm going to do is point out that this means that x squared is going to be equal to, z squared is equal to x squared plus y squared. And I'm going to make a substitution into the top equation here. So making that, we're going to get that x squared plus y squared plus x squared plus y squared is 16, or that 2x squared plus 2y squared is equal to 16. So x squared plus y squared would be equal to 8. This is going to be a circular region. However, the radius of this circular region is now going to be the square root of 8, which is going to be 2 square roots of 2. However, that said, the region is still circular, and that is the big indicator that we want to convert this into polar coordinates. So what I'm going to say is let's convert x and y into polar. So x squared plus y squared plus z squared equals 16. Can now be expressible as r squared plus z squared is equal to 16. In the RZ trace, that's going to look like a circle, and given that this was a sphere to begin with, that hopefully isn't a surprise. Additionally, we have z is equal to the square root of x squared plus y squared. Making a substitution into polar coordinates, that would be z is equal to r. So now, analyzing the RZ trace, let's take a look at those two things. Keep in mind that this circle is supposed to be the upper boundary, bounded above, and the line is supposed to be the lower boundary, bounded below. So here's the r-axis, xy plane, and the z-axis. So r squared plus z squared equals 16 is going to be simply a circle of radius 4. And if I were to take this and rotate it about the z-axis, I would get the entirety of the sphere. We also have the line z equals r. The line z equals r should just have a slope of 1. And we already know where this point of intersection is because we calculated that back here. That was our 2 square roots of 2 that we did. Now, given that the sphere is supposed to be the upper boundary and the cone is supposed to be the lower boundary, this would be the region in question. So if I take this and rotate it about the z-axis, that is going to give me the snow cone shaped solid, I guess, that we would need here. Now, it is technically still a round region, so we could convert it from cylindrical coordinates to spherical coordinates. I do want to point out, though, that it is possible to set this up using cylindrical coordinates and just leaving it as it is. Z would be bounded above by the sphere and below by the line. Solving the sphere for z would give us the square root of 16 minus r squared. And we only need the top side of it since we're only dealing with the top side. The lower bound would be z equals r. R, we showed, would go from 0 to 2 square roots of 2. And then theta we can get from the xy trace. That's going to be one full trip around the xy plane. So that'll go from 0 to 2 pi. So this is certainly one possible way to do it. However, this does also convert pretty nicely into spherical coordinates. So if we started with r squared plus z squared is equal to 16, r squared plus z squared is supposed to be rho squared. That would be rho squared is equal to 16, which would give us simply rho is equal to 4. Now, given that we started with a sphere of radius 4, hopefully that's not too big a surprise. We also had the cone, which was z is equal to r. Converting both of those into spherical coordinates, this would be rho times the cosine of phi is equal to rho times the sine of phi. Dividing both sides by rho gives us that the cosine of phi is equal to the sine of phi. Now, given that phi is bounded between 0 and pi radians, it will be necessary that this is either a quadrant 1 or quadrant 2 angle. Now, the only place in quadrant 1 where the x-coordinate and y-coordinate are equal to each other on the unit circle would be at phi equals pi over 4, which is pretty typical as far as a cone is concerned. So in spherical coordinates, we would be taking the same region and bounding from the pole to the outside. Then phi would be bounded like this, and then theta would be the same as before. So in spherical coordinates, we would be going from the pole out to the sphere of radius 4. So that would be from 0 to 4. Phi is bounded on the lower side by phi equals 0, which is the z-axis, positive z-axis, and going over to the cone. So once again, that would be phi equals 0, that's the positive z-axis, and then it rotates over until we get to phi equals pi over 4. So phi equals pi over 4, that's here, and phi equals 0 is right there. Do keep in mind that it is kind of counterintuitive to the unit circle because we're starting at the vertical axis and rotating in a clockwise fashion. So again, a little counterintuitive. Theta is then going to go from 0 to 2 pi. So using these two sets of bounds, I'm going to set up our original triple integral in both cylindrical coordinates and spherical coordinates, and then we'll make a decision about which one of those we actually want to do. So recopying this down, this was the triple integral over the solid E of z times the square root of x squared plus y squared plus z squared dv. In cylindrical coordinates, theta would go from 0 to 2 pi, r would go from 0 to 2 square roots of 2, and z was a little bit complicated. That went from r to the square root of 16 minus r squared. And then converting x and y into polar coordinates here, this would be z times the square root of r squared plus z squared, r dz dr d theta. So this would be cylindrical coordinates. Certainly not impossible. I believe for our first integral with respect to z, you would probably want to do a u substitution for that, and hopefully these turn out pretty nicely. If you did want to go with spherical coordinates, though, theta would still go from 0 to 2 pi. Phi would go from 0 to pi over 4. And rho would go from 0 to 4. Z would be rho times the cosine of phi. The square root of x squared plus y squared plus z squared would be the square root of rho squared. That'll be rho. And then dv is going to be rho squared sine of phi, d rho, d phi, d theta. Now, without doing any of the math, I can basically guarantee you that spherical is going to be nicer. And the reason that I believe it's going to be nicer is we can apply Fubini's shortcut. Just the greatest thing since sliced spheres, I guess. So applying Fubini's shortcut, we'll start with theta. That'll go from 0 to 2 pi. There are no thetas in here, so we'll just grab the d theta from the end, or we can call it 1 d theta. As far as phi is concerned, we have a cosine of phi and a sine of phi, and phi is supposed to go from 0 to pi over 4. It'll be the cosine of phi times the sine of phi d phi. Times, let's count the rows. Rho, rho, rho squared. That'll be the definite integral from 0 to 4 of rho to the 4th d rho. Fubini's shortcut is pretty fantastic. So first integral, that'll be theta going from 0 to 2 pi times. Off the top of my head, I can think of 3 different ways to do this. I think a u substitution with u equals the sine of phi is probably going to be the most straightforward one. So this will be 1/2 times the sine squared of phi, going from 0 to pi over 4. You could also do a u substitution with u equals the cosine of phi, or you could apply the identity that the cosine of phi times the sine of phi is 1/2 times the sine of 2 phi, and go from there. And then finally, 1/5 times rho to the 5th, going from 0 to 4. Plugging in these bounds, we have 2 pi times 1/2 times sine of pi over 4 is going to be root 2 over 2, and sine of 0 is going to be 0. So root 2 over 2, quantity squared, and that's all we need. We'll also have 1/5 of 4 raised to the 5th power. That'll be 1024. So let's see if we can simplify this. We can take out a 2 with a 1/2. We'll have a pi left over. This is also 1/2. Half of 1024 is going to be 512. Still have a pi, and that'll all be over 5. So final answer for this one. If you are interested in a nice little challenge, go ahead and try out this cylindrical integral and see if you wind up getting the same result as what I got doing the, well, the easy way.